Hi, this is an example problem that I will show you how to solve. I intentionally picked a few tasks that seem to be basic, but not very easy if you do not know techniques that we will learn in the future lectures. For example, how to convert state space representation into a transfer function. So here is one simple second-order continuous time system with matrices A, B, C, and D. And just to remind you that the dot denotes the time derivative. First, we would like to find a single ordinary differential equation that describes the same system. This differential equation should include output y and the input u, but should not include variables x. First, we start with writing the state equations explicitly. The x1 dot and x2 dot equal to matrix A times x1 and x2 vector plus b times u. The second equation will be y equals c times x plus 0 times u. So, to write this explicitly, x1 dot is equal to the first row of A times the vector x, which is 0 times x1 plus 4 times x2, and plus the first element of B matrix times u. Similarly, for the second equation, x2 dot is equal to 1 times x1 plus 0 times x2 and plus 0 times u. To compute y, we multiply the vector c by vector x and get 1 times x1 minus 2 times x2. Since we will need all derivatives of the output y up to the system's second order, let's try to compute them. We start with taking a derivative on both sides of the y equation. So y dot is equal to x1 dot minus 2x2 dot. Now we substitute state equations for x1 dot and x2 dot and get y dot equals to 4 times x2 plus u minus twice x1. Now let's take one more derivative on both sides of that equation. We get y 2 dots is equal to 4 times x2 dot plus u dot minus twice x1 dot. Again, we substitute state equations instead of x1 and x2 derivatives, and what we get is 4 times x1 minus twice in parentheses 4x2 plus u dot, and this equals to 4x1 plus u dot minus 8x2 minus twice u, and it equals to 4 times x1 minus twice x2 plus u dot minus 2u. But pay attention that x1 minus twice x2 is actually y. So this y could be replaced here, and we get actually differential equation only with y's here. So the differential equations that we get is y2 dots equals to 4y plus u dot minus 2u. And finally, we get the differential equation in the forms that we would like it to have. And this is y2 dots minus 4y equals u dot minus 2u. Alright, so we completed the first task. Now, the second task is to find the transfer function of that system. To find the transfer function, we just need to take Laplace transform on both sides of the differential equation. So we're replacing every dot with multiplication by s. So what do we have here? y2 dots is replaced with s squared times y of s minus 4 times y of s, and on the other side we have s times u of s minus twice us. Now we can combine s squared and 4 together in parentheses, and we get s squared minus 4 times y, and on the other side we're also combining s and 2, so we get s minus 2 times u. But h of s, which is a transfer function, is defined as y divided by u. So as you can see from that equation, algebraically you can get that the transfer function is s minus 2 divided by s squared minus 4. Or you can even simplify that and cancel s minus 2, and you will get 1 divided by s plus 2. Alright, so we got the transfer function, and transfer function after cancellations of zeros and poles. Now we want to check system stability. To check system stability, which is asymptotic stability, and BIBO stability. First, we're checking the transfer function before the cancellation. Since you have one of the poles at +2, which is +2, the system is not asymptotically stable. It's asymptotically unstable system. But after cancellation, the only pole which is left is at -2, which means that the system is BIBO stable. And we completed the task number 3 as well. Finally, the last task is to draw a block diagram of the system given the equations that we have in the system. Now, block diagram is built typically from amplifiers, integrators, and adders. So these are the 3 types of blocks that we accept in any kind of system diagrams. So we will start with the original state space equations of the system for x1 dot, x2 dot, and y, and we will try to develop a diagram which is showing how this system is working as a block diagram, and this diagram will be also useful for Simulink implementations that you will be using later. Alright, so how you start drawing block diagram? First of all, you're drawing the input U from the left and output Y arrow on the right. Then you put number of integrators, and integrator is a block of 1 divided by S, because Laplace transform of 1 divided by S is integration operator. So you plotting as many blocks as you have order of the system. So if the system is second order, you need to plot 2 blocks of integrators. The input of each block will be x dot and output will be the x. So on the left block we are drawing x1 as the output and x1 dot as the input. For the second block we are drawing x2 dot as the input and x2 as the output. Now let's try to implement the equation number 1, which is x1 dot equals 4x2 plus u. So we're taking 4 times x2, so multiplying x2 by 4, and then returning that line and that arrow and adding u to get x1 dot implemented. To implement x2 dot, we just need to connect x2 dot to x1, which is output of the first integrator, to the input of the second integrator. And that's it, this is implementation of that equation. To implement y, we need to take x1 line and to move it towards the y, and then we're subtracting twice x2, so we're multiplying x2 by 2, and then subtracting that from x1, and then we are getting y. Basically that's it, we implemented that system as was described by the equations. Thank you.